the friendly environment and the high level of mathematics make this place quite unique. So yeah, in these lectures I would like to discuss a particular topic that is how much can we retrieve about a group when we see its the left-right action of the group on its unchecked boundary. In particular, I would like to address some questions related to unitary group representations and in particular to the structure of operator algebras associated to the group. And so since this conference is aimed to be an intersection between dynamical systems, operator algebras, and unitary group representations, my idea is to start in the first lecture with a very introductory material in order to fix notation and also in order to give motivation to people that maybe come from different backgrounds, that is not operator algebras and analytic group theory. So the paradigm, let's say, the very general idea is the following, that we have a group gamma. In this talk, otherwise specified, gamma is always a discrete, countable, exact, sometimes ICC, if I forget to say it. Okay. So the idea is that we want to study our group. In particular, we want to study it through the lens of unitary group representations. So this is sometimes called analytic group theory. And so we have our group, and we are interested in all the possible homomorphisms from the group to the unitary operators on a certain complex Hilbert space. So something that happens, and it's very vague at this point, but something that happens is that this is very much related to the study of dynamics on certain spaces, in particular of boundaries. So this is related to actions of the group on boundaries of certain discrete spaces. One thing that I want to say is that here, for the study of analytic group theory of a group in this particular way, usually a tool that is used, or if you want a language, is the language of operator algebras. I will define something in a moment. Just to give an example of this connection, there are many, of course, also Bahir explained very much this connection. One example is the recent results in the Galanter-Kennedy approach. So basically they understood the following, that if you take a discrete group, then you can associate to it this what is called the Furstenberg boundary. And the Furstenberg boundary was defined by Furstenberg, and it's a universal object. It has this property that it is a compact space on which the group acts, and the action is minimal and it's strongly proximal. This means that for every measure, if you look at the orbit of this measure, the closure contains a delta, and it's universal among all these spaces, in the sense that every other compact, minimal, strongly proximal space is a factor of this. And they understood that this universal property, which characterizes the Furstenberg boundary, is the same as the universal property which characterizes the equivariant injective envelope of the complex numbers. That was a concept introduced by Amana, and they pushed this analogy further and obtained some deep results. For example, some basic results that they obtained is that the reduced sister algebra of the group is simple if and only if the group acts freely on the Furstenberg boundary. And another important result is that the group is exact if and only if the action is amenable. So for me, amenable will always mean topological amenable. So in the sense introduced by Clara Nantraman de la Roche, and it's the sense that Schimma used in his talks. Okay, and they also would address the question of how many traces we have on the reduced group sister algebra, and show that there is a unique trace if and only if the minimum radical is trivial. By the way, this is a clear evidence of the fact that studying certain dynamics can give information about unitary group representations. Now, before going on, since maybe people might be not very familiar with this, I will give an introduction to this topic. So the idea is really, so it will be a bit boring for people in operator algebras, but maybe for other people it will be, I don't know, a motivation at least. So the idea is that we have our group, and first of all we want to construct some operator algebras out of this group. And later on we will see why this should be sensitive. This should be something that really tells us something about the group, something interesting. So the first step is to take what is called the group algebra, and this is defined just as the finitely supported functions from the group to the complex numbers. So this is certainly.
Can you try a different chalk? This.
It doesn't work so good. Yeah, had my favorite chalks in Rome, but I forgot to bring the Japanese ones. You know? So let's try with this.
Try pressing a bit more.
Yeah, maybe. Yeah. Thanks. So this is certainly a complex linear space over the complex numbers. And we would like to give it an involutive algebra structure. Now, at the end, okay, we would like to construct some operator algebras that are in some sense the completions of this. And at the end, we would like to retrieve as much information as possible about the group. So the natural way to put an algebra structure is to put the group structure in the most natural way. And so we declare that delta gamma times delta gamma prime should be delta gamma gamma prime. So at this level we extend, we have an algebra, and now we would like to have an involution. Now, at the end, we would like to let's say, to study unitary group representations, and so the most natural way to give an involution is to declare that the group elements are unitaries in a certain sense. And so we declare that delta gamma star is equal to delta gamma to the minus 1. This gives to this linear space an involutive algebra structure, and now we will see how to produce operator algebras out of this with this. So the first step is the following. We take pi, that is a unitary group representation. So this immediately extends to an involutive algebra homomorphism that I denote by pi again. And this will take value in the bounded operators on the Hilbert space. Now, given this, the most natural way to produce a sister algebra is to complete with respect to the operator norm. So we define C star pi of gamma to be just the completion in norm of this. And this is certainly a sister algebra. Another way to produce a sister algebra is to take, instead of the the closure in the operator norm, the closure in the weak norm, the weak topology, for example. And this is particularly useful when you take a particular representation. So this is pi okay, this is what is called usually, is the prototype example of a phenomenology. Okay, so at this point we saw at least that we can construct operator algebras out of unitary group representations. Now, okay, we have to answer some questions now. The first question is if there are unitary group representations, if there are some, if there are enough, if they are sensitive of something. And this is not a trivial question, because for example, if you take a group that is second countable, a topological group that is not locally compact, then it's very difficult to find the unitary group representations. By the way, we are in the case of discrete groups. We will just take a list. Let's see if we can exhibit some unitary group representation. So the first example is the trivial representation. So this sends every group element to the trivial element in the group. Of course, this it's not very interesting to look at the operator algebras we obtain because we always obtain the complex numbers. But this will be important in the way it relates to other unitary group representations. Now, another example is called the left regular representation. It's a representation on L2 of gamma, where this is the L2 with respect to the counting measure. And this defined is just the left translation action. So it's defined in the following way. We take gamma eta in gamma, we take psi in L2 gamma, and we declare that lambda gamma psi evaluated in eta equals psi of gamma to the minus 1 eta. So in this way we obtain a C-star algebra that is usually called the reduced group C-star algebra. If we complete with the subnorm, if we complete with the weak topology, we obtain the group von Neumann algebra. And it's also quite interesting why people started to study this group von Neumann algebra. This was von Neumann and Martin studied that because they wanted to give examples of some factors. By the way, so we have the left regular representation. We also have the right regular representation because we also have a right action. And it's defined in the following way. We take rho gamma psi in eta. This should be psi of eta gamma. So in this case, the C-star algebra we obtain, it's actually a copy of the reduced group C-star algebra. But in these lectures, usually I keep denoting it in this way because I want to keep track of the relative position of these two C-star algebras inside the L2 gamma. So okay, we have at least 3 representations. How do I erase the blank? Now there is another class of representations that was already introduced by Bahir during his lectures. And they are called Koopman representations. So let me recall the construction. The construction is the following. Suppose you have a gamma acting on X locally compact, Hausdorff. And now, suppose for example that we have mu, the probability measure on X, that is invariant under the action. Then it's very easy to construct a unitary group representation. I denote it like this: pi mu of gamma. If I take, xi in L2 of mu, and this evaluated in psi in x is equal just to psi of gamma to the minus 1x for mu almost every x. So this defines certainly a unitary group representation, but now it's difficult in general to have measures which are invariant under the group action, in particular if you impose some regularity properties. If you have, for example, an action that is amenable and the group is not amenable, it's impossible. But we can relax this, and we can take a measure that is just quasi-invariant. So what does it mean, quasi-invariant? Well, it means the following, that you see we have an action of gamma on x. This gives an action of gamma on the probability measures on x, which is defined by transposition, let's say. It's defined in the following way. We want to say who is gamma mu. In order to say who is gamma mu, we have to say when we evaluate on a continuous function, what is the result. And so we apply this to f, and this is just mu of f composition gamma. So this gives an action on the probability spaces. So we have, these are the probability spaces on the probability measures on x. Now, if a measure is invariant, means exactly that this measure mu is a fixed point for this action. If a measure is just quasi-invariant, it means that if we look at the orbit, so gamma mu under this action, this is contained in the equivalence class of the measure. So it's where the equivalence class is intended in the sense of absolute continuity. And this just means if you want to check if a Borel set has measured 0, it's equivalent to checking that every translate of this Borel set has measured 0. So under this assumption, you see we are inside the equivalence class, and so we can take Radon-Nikodym derivatives, and so we put it here. And this gives a unitary group representation. And now there are plenty of these. For example, if you take G, that is a locally compact group, you take H in G, that is a closed subgroup, take gamma in G discrete, then you see you can do the following. You take the quotient, the coset space, G over H. In general, if H is not normal, this will not have an invariant measure. But what one can prove is that there is an analog of the R measure, and it is quasi-invariant. It's not invariant. So you take a probability measure in the same measure class, and you have an action on this. That is non-singular. So this just non-singular means that this measure is quasi-invariant. So in general, we are talking about many representations. Okay. So now the last bit of representations that we can construct, they're explained very well in a paper by Brown and Wentner. They wanted to construct what are called exotic group sister algebras. And so this will be useful in the next lectures. And the idea is the following. So we take I inside L infinity of gamma, a bi-invariant ideal. So bi-invariant means that it is invariant under the left and the right transposition. So we start with this. let's assume that this contains finitely supported functions on the group. It's not necessary, but it will be, it's easier in this case. So now, given this ideal, I tell you what is...
Contains or contain?
Sorry?
Contained or contain?
Oh, sorry. Yeah, thank you very much. Yeah. So now take a unitary group representation, and I tell you what it means that it is an I representation. So this is an I representation if, so we have this Hilbert space, we can find a dense subset in the Hilbert space such that whenever you take any two vectors in this dense subset, we look at the matrix coefficient. So the matrix coefficient is the function which sends an element gamma to the scalar product, pi of gamma psi eta. So this is certainly a function in L infinity of gamma. I want that this function is in the ideal. This is the definition of an I representation. And now, given this, we can construct a C-star algebra out of this. What is very important here is that the ideal is algebraic, is not closed. This is an important point. It makes a difference. So now we can construct a C-star algebra out of this. How? Well, we do the following. We define for F in the group algebra, I define the norm of F, the I norm of F, by definition is the sup over all I representations of the norm of pi of F. Now, why is this a norm? Well, we have to check two things, basically. The fact that it distinguishes elements. If an element, if this is 0, then the element is 0, and this is actually a consequence of this assumption. So I wanted to give it. And okay, and that it's bounded is clear because C of gamma is generated by unitaries, and every unitary has norm at most 1. So this is actually a norm. Is it a C-star norm? Yeah, because I mean, every of these gives a C-star norm, and so this is actually a C-star algebra. So we complete, and we obtain a C-star algebra that we denote C-star I of gamma. Okay, now for some examples of this construction. If you take C-star CC of gamma, this is just the left, the reduced group C-star algebra. And now you see the importance in considering algebraic ideals is that you obtain something different if you take the closure. Indeed, if you take C-star C0 gamma, this is equal to the... I didn't define, sorry. So, in the case in which we take I to be exactly L infinity of gamma, what you obtain is what is called the full group C-star algebra. And we just denote it by this. Okay, and this is the biggest possible C-star algebra you can obtain. So if you take now the ideal that is C0 functions, this is equal to the full group C-star algebra if and only if gamma has Hagerup property. So Hagerup property it's a sort of low rank. Okay. So, by the way, this is to say that it's important to distinguish between closed ideals and algebraic ideals. And another interesting feature is that, there is this, so C-star I gamma is equal, let's say like this. Gamma has property T, whatever it means. If and only if, whenever you have that C star gamma is equal to C star I gamma for some ideal, this implies that the ideal is everything. Okay, so this is just to say that this construction by Brown and Wentner, but what was known before, I think, it's something interesting at the theoretical level. Okay, so now we...
The reduce is always a quotient, I mean, with your assumption.
Yeah, exactly. This is why I just to have a faithful norm. I mean, otherwise, one take just the image and you have a norm there. Yes. So now, what we did so far was just to check that we have many unitary group representations, to construct C star algebras out of these unitary group representations. And now, okay, maybe we are doing this just for fun. We like thinking about it. But, okay, the trivial example, the most natural example in which we see that this analytic point of view really tells us something about the groups is, of course, amenability. So let me briefly recall something about amenability. So, okay, amenability was introduced by, I think, Tarski was the first one who checked this. He introduced the concept of paradoxical groups. And then Tarski and von Neumann understood very well what is an amenable group. So what is the starting point? The starting point is this Banach-Tarski paradox that tells you that if you take the sphere, the unit sphere in the three-dimensional Euclidean real space, then you can decompose it in pieces, a finite number of pieces, very particular pieces, such that whenever you apply a translation composition with rotation to each of these pieces, if you choose this translation and rotation wisely, at the end you take unions and you obtain two copies of the original sphere. And then, I mean, this phenomenon is one of the reasons why we define measurable sets in a certain way. And if you look at the proof, the group theoretic content of this is the fact that the free group on two generators embeds in a very, very strange way inside the rotation in three dimensions. And so Tarski and von Neumann were interested in understanding this phenomenon, and they defined what is called an amenable group. So gamma is amenable if there exists an invariant mean. So if there exists a state phi on L infinity of gamma such that phi of f composition gamma is equal to phi of f for every f and for every gamma. Okay, so and the point is really the fact that the free group on two generators is not amenable. But let's see so what is really this property? Are there amenable groups? How many non-amenable groups? And so on. Is it really something that, are we really talking about an interesting property of groups? So let's see. First of all, there is this approximation. So we have this invariant mean. Now, using basically Banach, one can show that phi can be approximated by L1 functions. So actually, probability measures on the group. And if you take wisely level sets of these functions, you can actually restrict to characteristic functions of finite subsets. And these finite subsets are called Follner sets. Since I assume that the group is countable, it's really a sequence, and we have Fn such that, so these are called Follner sets, and these satisfy the following, that if you take an element gamma in the group, so for every gamma, if you take you move Fn by the action of gamma, and you take what is called the symmetric difference with the Fn, you take the cardinality, you divide by the cardinality of Fn, this goes to 0 for n which goes to infinity. So with this, and this is actually equivalent to the existence of this invariant mean, and with this definition it's easier to find some examples. For example, the group of integers is amenable. And this is because we can take Fn to be just the ball of radius n. Now, one can extend to groups with sub-exponential growth. And also one can take some constructions. For example, if you take a semi-direct product, A semi-direct product B is amenable if and only if both are amenable. Okay, so at least we know that the class of amenable groups is rich enough. Is it true that the class of non-amenable groups is rich enough? Yeah, because as I told you, F2 is not amenable. So now I want to give a proof of this, and mainly because I want to introduce the Cayley graph. So already Hannah explained very well the Cayley graph of a group. But let me remind you what it is. So the idea behind the Cayley graph is really that we have a group, we put it inside a metric space, and we do it because in this way we can try to understand the properties of the group by looking at geometry. This is the idea. And in this case, it's very easy. It's a tree, and it's constructed in the following way. We take one vertex that is the identity, then we take an edge connecting the identity to one generator. So suppose this is generated by A and B. So this is A, here we have B, here we have A to the minus 1, here we have B to the minus 1, and now we go on. So if we go up, we have B, so we put AB, here A squared, here AB to the minus 1, and so repeating this process, we obtain an infinite graph, an infinite tree, and so on. So now we have this. So at the end we have all the reduced words in these two letters, and now I take some subsets. I divide this in 5 sets. So we have the identity that is here, and I call, for example, this S of A. Now you see, so S of A is the subset of all reduced words which begin with the letter A. So suppose phi is an invariant mean. Then, okay, phi cannot be supported on the characteristic function of the identity because the identity is translated, and so it should give positive mass to one of these sets. So suppose that it gives positive mass to S of A. So since this is invariant under translation, we have that phi of this should be the same as phi of a to the minus 1 of this. And this is just phi of chi a to the minus 1 S of A. But what is this set? You see, here we are removing the first letter, and so what we obtain is everything except S of A minus 1, because the only restriction that we have here is that we have reduced words, so we don't have A to the minus 1 after the A. So in particular, this contains, this set contains S of B union S of B minus 1. So in particular, the measure of these two sets should be 0. Okay, but then we repeat the same argument. We do phi of b to the minus 1 chi S of b. This should be 0, but now this set will contain S of a. And so it's a contradiction. So this will contain. So okay, the free group on two generators is not amenable, and every group containing a copy of the free group on two generators is not amenable, and it was actually an open problem. I think that Grigorchuk proved that there are non-amenable groups which do not contain the free group on two generators. I think it was him, right?
Oh, no.
No?
No.
Someone else.
Sansky.
Okay, thanks. Sorry. Okay, so this is to say that when we are dealing with amenability, we have a large class of groups which are amenable, a large class of groups which are non amenable. So we are talking about something really. And here, the theory of operator algebras is, for some reason, really reveals this structure. So in the book by Brown and Osawa, they say that there are at least 10 to the 10 to the 10 characterizations of amenability. And then we give 5. So, before doing that, sorry, I have to recall a relation between representations that is called weak container. So, suppose we have two unitary group representations of the same group, pi and rho. We say that pi is weakly contained in rho, weakly contained, if we have the following. So there exists a surjective star homomorphism from the sister algebra of rho to the sister algebra of pi, so surjective, such that, so call it phi rho pi, such that if we look at phi rho pi evaluated in rho gamma, this should be pi rho gamma for every gamma. Or equivalently, a more concrete, let's say, definition is the fact that you can approximate matrix coefficients from coming from the smaller one with matrix coefficients coming from the bigger one. So for every epsilon greater than 0, for every finite subset in the group, for every element in the Hilbert space of the small representation, that is H pi, there exists a finite number of vectors, eta 1, eta n, in the bigger Hilbert space, such that when we look at the matrix coefficient, so pi of gamma xi xi, this is approximated by this sum of matrix coefficients. So minus the sum I from 1 to n, rho of gamma eta I is less than epsilon for every gamma in the finite subset. And if you want, it's also equivalent to this other characterization that you see now. Every of these sister algebras is a natural quotient of the full group sister algebra by definition. And so we want the following. We take the full group sister algebra. This has a natural surjection onto a sister rho gamma. Also has a natural surjection onto sister pi gamma. This commutes, and this means that, so there is an ideal here associated to this. There is an ideal here associated to this one. And the requirement is that this ideal is contained in this other ideal. Okay, these are three equivalent characterizations of weak containment. And so, okay, let's get back to amenability. So the following are equivalent. Gamma amenable. The natural surjection from the full group sister algebra to the reduced group sister algebra is an isomorphism. The reduced group sister algebra is nuclear, where nuclear was already defined in other lectures. I don't want to give the definition, but it basically means that it's approximately finite dimensional in a certain sense. So you can approximate finite subsets by, okay, you can approximate this sister algebra by finite dimensional sister algebra in a certain way. This, and also that the trivial representation is weakly contained in the left regular representation. And the last one is that the group von Neumann algebra, that I recall is the weak closure of the reduced group sister algebra inside the project of gamma. This is injective. Injective just means that there exists what is called the conditional expectation from B of L2 gamma to L gamma. So it's a projection of norm 1. It's a UCP map, which is the identity here. Okay, so you see, if we look at this result, it's quite, I don't know, it's quite interesting. There is something deep that we are understanding, because we introduce these operator algebras kind of for fun, but at the end we see that at least for amenable groups they really encode this notion very well. And actually, if you take the group that is ICC, there is only one of all the group von Neumann algebras you obtain are the same, and they are the hyperfinite Q1 factor, and it's called R, and nobody knows why it's called R. But as we were discussing with Bach here, von Neumann always gives some very strange definitions.
Yeah, bad definition. Bad notation.
Okay, so this was to say that we started with an approach that is we try to understand a group.
But how is it when gamma is amenable and So the reduced C-star algebra, does it, is there an example where it's really, yeah, the question, I mean, does it somehow, what does it contain, I mean, about the group structure? I mean,
Nuclearity.
No, my question was, if you have two amenable groups, torsion-free, with the same reduced C-star algebra,
Oh, if they're the same.
or not, I mean, I don't know, are there examples?
Oh, I don't know about this.
Are there some examples where they are the same? Or,
Yeah, I never thought about this. Yeah, I never thought about it. I don't know, honestly.
you said on the level of fundamental algebra you're not going to get anything. I mean, at least.
Yes.
We can. The level of reduced C-star algebra, is it?
It was stated as the open question in Papawa's paper.
Sorry?
It was stated as the open question in Papawa's annual paper. Whether it's true or not.
So it's open, okay. That means it's.
Thanks. Yeah. So yes, so we introduced this approach, and we saw that in this particular case it gives something, and now we would like to understand if maybe we can leave the realm of amenable groups and see if we can obtain some result in the same flavor. Now, in order to do this, so in particular, if we can look at groups that are not amenable and study some notion of amenability, in particular for actions, and see if we can deduce something about the structure of the operator algebras. So let me briefly recall what is an amenable action. Okay. So, definition. So here I will basically only consider actions on compact spaces, but it's not necessary. We said that the action is amenable if there exists a net of continuous functions from X to the probability measures on gamma, such that for every gamma in gamma, we do the following. We take gamma mu I is the translation of the measure that I defined before, evaluated in X. So in X it gives a measure and I translate the measure, minus mu I of the translation of X. This should be small in the sense of the one norm in the probability of gamma, and we take the sup over X in X, so this should go to 0 in the net. So you see, this in particular group is amenable if and only if the action on the one-point space is amenable. And in this case, so Claire proved that we have something similar to that theorem, de la Roche. And we have that, so the following, gamma on X amenable. This implies, it's actually the same as the reduced cross product is amenable, is smoother. So what is the reduced cross product? Okay, it's the following. So it's a generalization of the reduced group C-star algebra, and it's defined by using, instead of unitary group representations, covariant representations. And so if we have this action, we can consider pairs of representations from C of X gamma to a certain Hilbert space. So we have the representation of pi of C of X and the representation rho of the group. And this is covariant if pi of f composition gamma to the minus 1 is equal to rho of gamma pi of f rho of gamma to the minus 1 for every f and for every gamma. This defines a notion of covariant representation. We can take the soup. So we define an analog of the group algebra. In this case, it's exactly as in the case of the group. And we obtain the full cross product. And the reduced cross product is defined by taking, we fix a faithful representation of C of x. And we take as a Hilbert space L2 gamma tensor product this particular Hilbert space. In this Hilbert space, we represent C of x as diagonal matrices, in which at the entry, let's say gamma, so gamma is the element here. This entry is F composition, I think, gamma, and so this is the representation of the continuous functions. And the representation of the group is just translation on this. So the group elements are sent to lambda gamma tensor 1. So this gives a covariant representation. One takes the completion of this algebra, obtains what is called the reduced group system algebra. Okay, so in the case of amenable action, we obtain something similar to this. And this implies also that the natural surjection on the full cross product to the reduced cross product is an isomorphism. And also implies that the von Neumann algebra is the weak closure of this is injective. By the way, so this was just to recall these properties, and the reason why I recall these properties is that we want to look at a particular action. What is the topic of these lectures is really to look at the following action. We have an action of gamma on itself by left translations. We also have an action of gamma on itself by right translations. They commute, and so we have an action of the Cartesian product. Gamma times gamma on gamma. And this is left times right. So this action gives rise to an action on the stone-check boundary. So now usually, maybe I'm going to, but I find it difficult sometimes to find references for the stone-check boundary. Sometimes it's not, it's a universal object and so on, but I think I want to spend some minutes recalling the definition, because I don't know, usually sometimes people don't know what it is and so on.
I think it's not taught now in topology courses, probably. But
It's
good to be.
So also because in some cases I really need to see concretely what we are doing on the stone-check boundary. So I would like to recall something about it. So what is the stone-check compactification? I will be interested only in the case in which we have, let's say, S, a countable set. This is the only case I will consider. So, I tell you what is a ultrafilter. So, an ultrafilter on S is a collection of subsets let's call it omega, and this collection has the following property, such that first of all, if A is a subset of B, and A is an omega, then B is also an element of the ultrafilter. If we have two elements in the ultrafilter, then also the intersection is in the ultrafilter. The empty set is not an element of the ultrafilter, and these three define what is called the usually filter. And the last property that is very important is that for every subset, either the subset itself or its complement is an element of the ultrafilter. And now it's a very interesting fact that it's easy to construct filters, for example, Frechet filters. And given a filter, you can take, there is a maximality argument, you can use the axiom of choice to construct an ultrafilter, and nobody knows how to construct an ultrafilter explicitly. But we talk about it. Okay, so assuming the axiom of choice, there are one and there are many actually.
I mean, one principle.
Yeah, sorry, yeah, free ultra, yeah, sure, sorry, yeah. So, yeah. Okay, so now we have this set, and I denote it by this. Delta beta S is the set of ultrafilters. And I want to give it a topology. And the topology I give it is a topology generated by the following open sets. So we take a subset in S, and then we associate to it an open set that is the set of all ultrafilters which contain A as an element. It's a subset that is in this collection. I give to it this topology, and they are actually open sets. Now I tell you the following, that for every map phi from S to X, where X is a compact Hausdorff space, there exists a unique extension, continuous extension, that they call phi beta, from the Stonechek compactification to X. And the proof is very easy. So the proof relies on the following. So I tell you that if you give me an ultrafilter, there exists a point in X with the following property. For every open set around X, so open, the inverse image is an element of the ultrafilter. So why this is true? So suppose this is not the case. Suppose not. Then you see we have, this is a compact space. So we can find, so for every point I know that there is at least one open set around this point which is not in the ultrafilter. So I find a cover of this space by a finite number of open sets. So there exists U1, UN, such that phi to the minus 1 of Ui is not in omega for every I. But then, since they cover everything, we also know that the intersection of phi to the minus 1 Ui complement set is the empty set. And so what we found is that since this is an ultrafilter, the complement, but phi to the minus 1 of Ui, the complement of this is an element of the ultrafilter. And so this contradicts the fact that finite intersections of elements in the ultrafilter should stay in the ultrafilter, because the empty set is not an element. Okay, so this is easy to see that there is this point. Now, is it possible that there are more than one point? Of course not, because the space is Hausdorff. So since the space is Hausdorff, suppose we have 2 points with this property, then by the Hausdorff property we can find 2 open sets which do not intersect, one around one point and one around the other, and the inverse image should be both elements of the ultrafilter, and this is impossible because the intersection is empty. So this uniquely defines this map. Is it continuous? Well, yes. The continuity comes, for example, if you take C, a closed set, and then one can check that what is phi beta to the minus 1 of C. This is the intersection over all the open sets around this closed set of U of phi to the minus 1 of U. So these are all Klopen, so this is a closed set. So, okay, we show that this is the case. And, okay, now we have this map is continuous. Now let's see that this space is compact Hausdorff. And it's actually the spectrum of L infinity. So the second thing is that delta beta of S is compact Hausdorff, and is the spectrum of L infinity of S. So it's the space of characters. So this is for the Alpha duality. If you take the star homomorphism from L infinity of S to the complex numbers, and you give it the weak star topology, and this is exactly the spectrum. So how does it work? Well, the idea is the following. You take omega here. I want to associate a character to that, so to L infinity of S. So how? I take f in L infinity of S, and the character I want to consider is the following. You see, f now is a function from S to minus the sup of f plus the sup of f. So this is a map from S to a compact space, and I extend it continuously. So I consider f beta of omega, and this gives, one checks that this gives our character. Now suppose, on the other hand, that we have a character, so we have phi a character, and how do I define the ultrafilter? I declare that A is in omega if and only if phi of the characteristic function of this subset is 1. And one checks that, okay, these are one the inverse of the other, one checks continuity, but once we know the recipe, it's easy. So, okay, and this proves everything, because this is a compact Hausdorff space. So we know now that we have this particular compactification of a discrete set, and we will be interested in the case of the group. But now let me just tell you something. If you have so it follows really by this, by what we saw, that if you have a group acting on S, then this extends. So this the action is by bijection. this extends to a continuous action on the stone-check compactification by homeomorphism. Okay, but there is also more, that if we have now this action, suppose we have an equivariant map onto with an action on a compact Hausdorff space, then this also extends. So we obtain the extension is equivariant. Okay, and okay, the last bit of information is that so we have S. This is embedded into the stone-check compactification. What is the embedding? We take 1 point and we take the collection of all the sets containing this point. So this is what here, the principal ultra.
Yes.
So we take S, and it's easy to construct. So we take S, and we take all the collection of all the subsets, such that S is an element, and these are called exactly principal ultrafilters. And what I call the stone-check boundary, so I identify S with the subset of this, and this is the image. This is important. The image is a discrete, open, and dense. Okay. So I identify S with this copy inside the stone-check compactification, and I take the stone-check boundary just to be what is left. And this is the elements here are called free ultrafilters. Okay, so this is pretty much what I wanted to recall about the stone-check boundary. Now, how much time do I have?
10:45.
Okay, 20 minutes. So maybe I will start with really the topic of these lectures. If there are no questions. So now I'm interested in the following situation. That is what I want to study. So as I told you, I want to study the action of gamma times gamma, the extension of the left-right action on the stone-check boundary of a group. So I will study with a particular example, and let's see what we can say. So I will consider SL to Z. So the 2x2 matrices with the determinant 1 and entries in the real number. So what I tell you is that the action of SL to Z times SL to Z, this is basically due to Furstenberg. I tell you that the action of SL to Z times SL to Z on its stone-check boundary is amenable. And yeah, this is basically what I mean. So Furstenberg wrote a beautiful paper on the proceedings of probability. I think it was around the 70s. And quite interesting. So in these lectures, I'm mostly interested in the case of SL2Z and SL3Z. And quite interesting in that paper, Furstenberg, in that paper he explains very well what is the Poisson boundary of a group and so on. And one of the starting questions is the following. Is it possible to embed SL3Z as a subgroup of SL2Z? And of course the answer is no, but he shows that the answer is no. And in order to show that, he introduces these Poisson boundaries, and he shows that the dynamic is too different in order to have this. And that this contains some, the beautiful idea that if you want to study the local structure of a group, really the group structure, maybe it's convenient sometimes to look at infinity. And this is a revolutionary idea, I think. And this is basically the same that we do. So, okay, how do we prove that this is a mu? So, first of all, I define the following map. I take phi, so I will always, for me phi is everything, it's a function, it's a map. So in this case, it's the following map from SL to Z to the projective 2 by 2 matrices over the real numbers. So this is just, by this I mean 2 by 2 matrices quotient by the invertibles in the real numbers. So just a moment. Sorry. So now you see, this is a compact and a second countable space. And now there is a general fact. I want to extend this to phi beta from the strong check boundary to the same space, and they restrict to the strong check compactification, and they restrict to the strong check boundary. So now you see, this is a general fact. If you have a map, so you have this extension to this space, let's call it X, to X. Okay. Now you see, suppose we have this omega that is sent to a point X. Now, since the space is second countable, by definition of this map, phi beta, we can take a countable subsets, un, which detect the point. And for every of these un, you see, by definition, when we look at the inverse image in the group, this gives an open subset of this. So the inverse image at the level of the group should be an element of the ultrafilter. And so we can pick now a point in this subset that is an element of omega, and then we can do it in a countable way, in such a way that phi beta of omega is the limit over n of phi of gamma n. So this is something that you can always do when you have maps, extensions of maps from the strong check compactification to a second countable space. So now we know that there is a sequence converging to this. Okay. And now there is the argument by Furstenberg that he used in the paper that I told you. And the argument is very easy. So suppose we have gamma n which goes to infinity in SL to Z. So gamma n is a 2 by 2 matrix. An, Bn, Cn, Dn. Now I take the columns. So I call it, for example, Vn is An, Cn. And Wn is Bn, Dn. Now, since they should have all determinant 1, what we know is the following, that we have the following possibilities. So we draw, so suppose this is Vn and this is Wn. So the determinant is just the the area of this particular figure. This is one. And so when we go to infinity, up to a subsequence, there are not so many things that can happen. So either we have Vn that goes to infinity, and Wn stay bounded, or the other way, we have Wn that goes to infinity and Vn that stays bounded, or if they both go to infinity, they should converge in direction. So they should get closer and closer. And so what does it mean? It means that whenever we look at the limit of this sequence, so you see, if we take gamma n over the norm of gamma n, this converges to a rank 1 matrix. And so this map takes values in projective rank 1 matrix. But what are projective rank 1 matrices? So they are just the information of the range and the kernel. And all this is gamma times gamma equivariant, of course. So this map is SL sub Z times SL sub Z equivariant. So this is just the information of the range and of the kernel. And so it's a copy of the real projective line times the real projective line. And now the left action becomes translation of the range, and so all it takes place here. This is so the left action is just multiplication of matrices, and you send to the projective space. And the right action only takes place here. And now one has to prove that the action of SL sub Z on the real projective line is amenable. At least from Pagir lectures, we know that there is at least one, the Lebesgue measure is Zimmer amenable, but actually it's true for every quasi-invariant measure. And okay, so I will not prove it. But basically the idea is that this is an homogeneous space for SL2R, and the Gaussian group is amenable. And SL sub Z is a discrete subgroup of SL2R. These are amenable. By the way, this implies, so this action is amenable, this action is amenable, so the product action is amenable. And so it's easy to see that if you have this map is equivariant and goes on to an amenable space, then you have an amenable action, because you can compose. You just, in order to have the approximate equivariant means, let's say you compose. And so the action of SL sub Z.
So extension of amenable actions.
Yes, you just need a map, not even surjective. Yeah, a continuous map. Yeah. Okay, so we have 10 minutes, yeah. Maybe. So now this is a particular property that basically is just this observation by Furstenberg gives us this property, and it may seem that this property is I don't know, is it useful and what? And actually it's very useful, but we will see it probably in the next lecture. For the time being,
Actually, I proved that SL2Z on projective line. the action on positive line is amenable, topologically. Because I didn't use a measure. Or did we? No.
No, so if I remember correctly,
Yes, yes.
you proved it for the Lebesgue measure, using this particular, the fact that the irrational points have measured zero.
Zero. So there is this,
What you proved, I think, is that the action of the free group Poncho generators on the visual boundary is amenable.
Yes, it's topological.
I think so. Yeah. Okay, so 10 minutes. So
Yeah, but the free group is essentially SL2Z.
Yes, yes. They have the
We
same.
proved this in Bedlam.
You mean?
Yeah, it's a finite index. I mean, somehow I think it's probably. I mean, topological amenability is probably not disturbed by finite index. If you have a finite index subgroup, which is
So, but you proved the action of the free group Poncho generators on the visual boundary, right?
yes, yes, that's different.
But
right.
that's-
Okay, it's not. So there is something to be done there.
Yep. I think this is a quotient of the. But by the way.
Yeah, but it's because the
Yeah. So, by the way, so we found this property in this way, and now we want to elaborate on this. So the first thing, let's put this way. We have this particular property, gamma times gamma acting on the Stone-Check boundary that is amenable. We want to relate this property to regularity properties of a certain unitary group rep, and at the end to relate it to the structure of the phenomenon algebra of gamma. So this is what we would like to do, at least probably in the next lecture. Okay. But I think, yes, yeah, probably it's too much to do it now, but at least I want to discuss something about this. And it's a very easy argument. So, I recall you a notion that is the Calkin algebra. So, we take the following. Consider this star homomorphism. We take B of L2 of gamma, and we quotient by the compact operators. And this is, in some sense, is the non-commutative analog of going from L infinity of gamma to the Stone-Check boundary. This is. It's trivial that the continuous functions on the Stone-Check boundary of gamma is the same as L infinity of gamma over C0 of gamma. This is by Gelfand duality. So consider this, I call this Q of L2 gamma, and this is the Calkin algebra. So now you see, this is the non-commutative analog of the Stone-Check boundary. Now here we have something about the dynamics. We have this particular action that is amenable. What is the counterpart at the level of unitary group representations? It's the following. Consider the following unitary group representation. That is, we take, we want to go from gamma times gamma to the Calkin algebra. We do the following. We define, so from gamma eta, first of all, we take the left and the right representation. These are commuting representations, so give rise to a representation of the Cartesian product. We compose with the Calkin homomorphism. So this defines a representation. So this representation is tempered. By this I mean that is weakly contained in the left regular, in the lambda of gamma times gamma, whenever the action of gamma times gamma on the stone check boundary is a minimum. So, by the way, maybe I should have said, this property is very peculiar. Because you see, if you look at the action of gamma times gamma on itself, this will never be amenable. Because you have a subgroup that is the diagonal copy of gamma, which fixes one point. This action is transitive, and there is the identity element that is fixed by this subgroup. So amenability of this action is equivalent to amenability of the group. So what this result is telling us is that this degeneracy that you have locally becomes negligible when you go to infinity, and not only becomes negligible, not only the stabilizers of point are amenable, but there is much more, that you have this sort of hyperfiniteness of the equivalence relations associated to quasi-invariant measures. So this is a very particular property. And we will see that it's in some sense a low rank property. I have 2 minutes, 3.
Yes.
Okay, so but the proof of that result is it's quite straightforward. So you see, we have this. We have a covariant representation from this pair to the Calkin algebra that is just Q and Q composition lambda times rho. So since L infinity of gamma, the continuous functions on the stone check boundary is just the quotient of L infinity of gamma by C0 of gamma, and since Q restricted to L infinity of gamma is exactly this, is the quotient by C0 of gamma, what you obtain is a covariant representation of the continuous functions in gamma times gamma. So a covariant representation gives rise to the representation of the full cross product. So we have C cross product gamma times gamma and Q over 2 gamma. And now, since the action is amenable, this is the same as the same in the natural way as the reduced group C-star algebra, the reducer cross product. So we have this, and now
Is this delta beta gamma or delta f gamma?
oh, sorry. Yes. yeah, sure. This is the stone check boundary. Yeah. Sorry. Thank you very much. So we have a covariant representation from the reduced group C-star algebra, and so from the definition of what it means to be weakly contained, we see that now if you take an element here, if you take lambda gamma eta, this is sent to exactly Q composition lambda times rho of gamma eta, and so this is exactly the notion. We have to say that this contained naturally the reduced group C-star algebra. This is because, as Shimma said during the lectures, that it doesn't matter the Hilbert space, the faithful representation of this. So in particular, it doesn't matter the faithful representation of the complex numbers, and you can see them as a subalgebra. By the way, so what we saw is that this particular representation is weakly contained in the left regular. And okay, so I think this is enough for this lecture.
Okay, so let's thank Jacopo. Do you have any questions for him?
What about the converse of the last one?
Yeah, this is part of the project of my grant, and I don't know the answer. Yeah, and actually,
Hopefully not.
and actually,
Not yet.
also I mean, I will tell you about the structure of the phenomenon algebra, and this is something maybe you know, it's called solidity. And then
Because you get it's by exactness, right?
Exactly,
Yeah, yeah.
exactly. And these three are all open. We don't know if they're equivalent. If by exactness is equivalent to this property that I proved, that called the Ekman-Ostrom property, and the solidity of the phenomenon algebra. These three properties, we don't know if they're if you are the same. Yeah. At least I don't. Maybe you do, but.
I have a problem with the definition tempered. I mean, this is not a unitary representation, what you have.
Yes, it is.
What you mean is it factorizes through the reduced C-star algebra. So you have that's what we are saying, what you're proving, actually.
Yeah, sure, but it is a unitary group representation.
It's not unitary. Yeah, I mean,
the Kalkin algebra lives inside the Hilbert space. Right?
yeah, but it's a quotient what you have there.
No, but I mean every
You don't
every
have-
representation of of the full group C-star algebra is a unitary group representation because you restrict.
No, but you, I mean, first you don't have, you just have not something, not on the level of C-star algebra, you didn't define it, you defined on the group.
So maybe. So as this is a C-star algebra, I can embed inside some strange Hilbert space, and this gives a unitary group representation.
I mean, separable C-star, okay. Okay.
Non separable. Yeah, sure. But yeah, I mean it's.
Yeah, you view this way, okay. I thought just, I mean, it's probably better to, anyway, but it means that, I mean, that's the proof, I mean, what you gave.
Yes, exactly. The factorization result. Yeah, sure. But it's a matter of terminology. But this is what the continuity of this star homomorphism from the full group C star algebra with respect to the reduced norm. This is just.
All right, if there are no more questions, let's thank Jacopo again. We'll come back at 11:15.